Hello guys, welcome back to the channel. So today we have decided to come up with a new series wherein we would be seeing binary search right from scratch to advanced level. So we will try to make a note that we will be covering all the topics, all the basic questions that revolve around binary search and are mostly asked in an interview, and we'll be trying to get an intuition of how to solve these binary search questions by deep diving into the binary search algorithm, understanding it right from scratch, how we'll be dealing things, and then maybe you will be very confident on acing the interviews in a much better with a much better confidence actually. So let's start with binary search algorithm, how we are dealing with this. So let's take a small example and understand like how this binary search algorithm came into mind of any scientist who actually built this binary search algorithm, and how he thought around making the search operation much more efficient to use, rather than doing a linear search that actually cost around order of n time complexity and reducing it to log n time complexity. So let's take an example, the very basic example. I think most of you in your school days, you might have used a dictionary wherein your school teacher, your English teacher might have told you, okay, just find the meaning of this particular word that came onto your textbook. Okay, so in a very similar manner, let's say you have a dictionary right now in your system, right? You are in some machine language, or you're doing some project in a machine language, and you have made a certain set of words that are there in your system in a sorted fashion, right in a form of a dictionary. So let's say you are making a system that is efficient enough to tell you where a particular word exists. Okay, so you are trying to figure out the very same algorithm, the very same way wherein you yourself physically would be finding the same word in that dictionary if that was physically present to you. So let's say the search operation or the search space, not search operation, the search space over here is of 1,000 words, right? So if this was of 1,000 words, this entire space was of 1,000 words, and you were trying to find the word code, the position or the space over where this word code is present in your dictionary. So what would you do? If this dictionary was present to you physically, the one thing that you would do is you will open up any random page, any random page that is there in the dictionary, and you will see whether the word code is present or not. So let's suppose again you did the same, very same thing, and you end up over let's say you end up over here, and the word over here was van. Okay, so you made this note that I have landed over the word van, and if you see very carefully, the all the words greater than van, you actually don't need to make a search over there. So what you would do, you would never be going beyond this point, right? So this would be a waste for you. You will never be going in this direction and try to search your word code in this particular search, in this particular space. So what actually happened is you shrink down your search space from uh, around 1,000 words to, let's say, only about 600 words now. So you are just searching in 600 words now. So let's say again, you randomly chose a word from a dictionary, not chose a word, you randomly landed on a word that says ball. So again, you can think around it that, okay, my word definitely will not be present prior to ball. It will never land before ball, right? So this going backwards will actually does not make any sense because your word code is greater than ball. So what happened now is that you actually reduced your search space even more. And that search space, let's say it was 600. So now it came out to be around just, let's say, 200. So from 600, there is a drastic drop to 200 again. So if you can see, from 1000 searches, you brought down your search operation to 600. And now from 600, you are evidently going to a search operation for only 200 words. Right. So you can actually visualize that you are actually not going on to each and every page by page and trying to search a word code, rather than you are removing the search space. You are eradicating the search space by making the assumptions that, not assumptions, but yeah, a valid hypothesis that your word will definitely be not in this search, in the left search space, or it will definitely be at the right search space. So if this search criteria is understood, then I think this binary search algorithm works best, because it would never be in the complexity of order of n. So that would save a lot of time, rather than it might or might not space a lot of might be or might not be saving a lot of space. That depends upon the recursive code that you're writing, or you're writing an iterative code. So we'll be discussing that also in a while. So, okay, if this part is clear, now let's try to understand the very same thing by taking some numbers. So let's say you are given certain sorted numbers starting from 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So if I draw this little graphically, so this would be our graph. So 1 lies over here and 10 lies over here. So what I want you to do is, I want you to do the very same thing that you are doing in your dictionary. I want you to go to a very random place. Now, how would you would be getting to a very random place? Let's say we are not going to a random place, but we are just eradicating. We are just trying to reduce our search space to just half of what the entire space is. So if your starting is at 1 and your ending is at 10, so your first search space, if I say call this as SS, that is a search space, your search space is from 1 to 10. So what would be the middle value over here? So your middle value will actually be, if you add this up, 10 plus 1 and divide it by 2, that would come out to be 5.5. And if you consider only the integral part, so you'll be reaching to an index value 5. Right. So you came out to be here, and this position was actually 5. And you are actually trying to search for the value 2, where it is present. Okay. So once you land up at 5, doesn't it make sense that 2 will never exist at the right part, because all the values are actually greater than 2. Right. So we understood this particular case over here, that if let's say if a of I is greater than x, then we have to go left, right? A of I is our 5, and 5 is actually greater than 2. So we don't have to go to the right part, rather we have to go to the left part. So this is very much clear to us. And we found out the very first case that, okay, where we need to go. Okay, so our next search operation actually got reduced from 1 to 5. So what would be the middle value at this particular position? So that would be 5 plus 1 divided by 2, that is 3. And 3 lies over here. Let's say 3 lies over here. So again, this is the same if condition, right? We will again not be going towards right, rather we'll be going towards the left part. Right. So again, our search operation, our search space actually reduced from 1 to 2. Right. From 1 to 2, how many elements are there? What will be the middle element? So we do it by 3 by 2, and that comes out to be 1. So we land up at 1, and what we found, that 2 this time our a of I is actually less than x. So do you think we need to go backwards? We don't need to see at backwards. That is, we don't have to go towards the left. Rather, we need to search at this particular search operation, that is at 2, right? So next time our search space would become from 2 to 2. And if we do 2 plus 2 divided by 2, we will be landing at 2. And a of 2 at this particular point would become equal to x, and this would be our happy case that we actually found our um, element that we were trying to find in the binary search, and we will return this particular element back to the recursive call or back to the user who actually wanted to search for the element, right? So this was the entire algorithm, or this was the entire idea behind the binary search algorithm. So let's see some of the observations that we did. So there is one observation, one very important observation about binary search that we understood over here. So that would be, always consider search spaces, and try to reduce space search space at each call. So this is the very intuition that we have to keep in mind, that at each and every call, either we will be going towards the left or we'll be going towards the right. So at each call, we will be going towards left, or we might be going towards right. So this is the very intuition of binary search. Now let's just look into the code, pseudocode for binary search, and that would actually help us to understand how we are writing a code for the same. Okay, so let's say you were doing a binary search on elements for array with X as the search. And let's say initially your search space was from start to end, right? So when do you think what should be the base case? The base case should definitely be whenever your search space becomes invalid. So this is your invalid search space. How can the start be greater than end? Start can never be greater than end. If you reach at this particular position, then this means that you are never going to find your element, or the element does not exist in the given array or in the given search space, right? The very second thing that we did in the algorithm that we saw right now was finding the mid value. So finding the mid value was nothing but doing start plus end divide by 2. That is finding the middle value in the given search space. So we found the middle value in the given search space. And then the next part is to make decisions whether to go on to the right part or to the left part. So uh, before that, what was the very happy case? The happy case was it might happen that your mid value is actually equal to X. If this happens, then we can return the mid directly, right? The second case that was that if your mid value is actually greater than X. So let's see that again. So this was your mid value and your X is somewhere over here. So this means that your mid is greater than X. So it will never be lying over here. And we need to go at this particular position. So that means going towards the left. So if your end was over here and your start was over here, what do you think should be changed? Your mid value, your end value should be changed to mid minus 1. Because the reason why we are not including mid and we are taking mid minus 1, the reason for this is definitely not your answer, right? Mid is definitely not your answer. Then why to take mid as your end value and why not end minus 1? Sorry, mid minus 1. So that is a very idea that we always take mid minus 1, right? So we will do return, yeah, binary search and taking it as BS, array X and start till mid minus 1, right? So in the second, what was the last case? The last case was, last case would be if mid is actually less than X. So let's say, again, graphically, let's understand. If your mid was somewhere over here and your X is over here, so your X this time is greater than the mid value. So definitely your search space would be this now, and this can be neglected. We don't want this, right? So this time your start should actually be changed. So we would return binary search array X, and we would say mid plus 1 till end. And that's the end of the code. So this was a very idea behind the binary search. This was a very basic algorithm, the very genesis of binary search. In the later sessions, we would be definitely looking into good problems around binary search, and we'll be trying to make the intuition, the idea behind various problems, how binary search is actually being implemented. So we will be also seeing some of the questions where the arrays are actually not sorted, and yet we are applying binary search. So it is going to be really great journey. I hope you really liked the video. Stay tuned for more such videos on binary search and other interview questions. I hope you really liked the video. Do let us know in the comment section if you want any such video to be made on any of the topics. We would be definitely compiling all your suggestions, and we'll try to give the best that is there with us. Hope to see you soon. Thank you. Bye bye.